Well, now that the clock's working again. So, did you guys hear about the disaster that happened yesterday at the coin factory? It's pretty crazy. All of the machines just shut down spontaneously. All the machines that were making all of the quarters and nickels and dimes, tell you, it just did not make any sense. I appreciate the giggles. Okay, so let's take a look at the question. It is a bit longer, but at least it's in green, which is generally a happy color. You jump off a cliff and land in the water below at a certain velocity. Then you do the same thing, but from twice as high. How many times faster do you think you're going to be going when you hit the water this time? Anybody want to throw out any guesses for this one? That's okay. This is kind of a hard one. Did you have a guess, Caden? Okay. So if we're going to figure this out, let's just try and think of it in terms of energy. You know, if you're jumping off a cliff into water, what kind of energy do you begin with when you start up top on the cliff? Potential energy. So all of your energy is originally potential. At the end, right before you hit the water, what is all that energy transferred into? Kinetic, yeah. As Wile E. Coyote knows all too well. So if you want to find out how fast you're going, you just go m times g times whatever that original height is, set it equal to 1/2 mv squared, and then you solve for the v. Masses go away, and in order to solve for that velocity, it's just equal to 2 times g times that height y. And in order to get rid of that square for the velocity, we square root both sides. And that's what your velocity would be equal to. So now the question is then, how is this different if you start from twice as high? Well, if you start from twice as high, then this y would just be, 2 times y, twice that original height. So I would just start with a 2 out there, and the way it would change this is when you multiply both sides by 1/2, you'd have 2 times 2. So that is 4, of course. I'm going to leave it as 2, though, just to kind of help us find out what the answer to this question is. If this would be your new equation for how fast you're going when you hit the ground, this square root of 2 here is the extra factor by which you will have sped up. So you will be going square root of 2, bless you, times faster when you hit the water. If you jump from 3 times as high, you'll be going square root of 3 times faster. In order to be going twice as fast, you'd have to go by 4 times as high, because square root of 4 would be 2. So yeah, your speed increases by a factor of square root of 2, or 1.41, if you're a decimal person like me. Questions on this? Okay. So let's get into the new stuff. The new stuff is called power. So you can label your notes power. So a lot of things well, not too many actually. Some things in physics and science in general are quite different from how we would think of them in the real world. Like when we're talking about work, generally you don't think in the real world of work being equal to force times distance. or work being equal to change in energy. Usually think of it as something like effort. Power is one of those things that's pretty much just like what we would expect in the real world and the science world. So here's the thing. We've been talking about energy so far lately. And, you know, and work is simply equal to your change in energy. Now, when you're talking about that, change in energy would be the same regardless of how long it takes you to do something. So, like, if you start from rest and you go to 100 miles an hour, whether you do that in the span of 1 second or whether you do that in the span of 100 seconds, it's the same amount of work. It's the same change in kinetic energy. Same thing if you're changing your potential energy, because remember, work is equal to change in energy. So you can do change in potential energy just like change in kinetic. If you are pulling something upwards and it takes you, 1 second to do that, compared with 100 seconds, you have done the same amount of work. Because work is just change in potential energy. Whether it took 1 second or 100 seconds, it's the same amount of work. Power takes that change of time into account. So if it takes you 1 second to, pull up a bowling ball 1 story, if you've got a bunch of people that are pulling up a bowling ball or something like that, that is going to be more power than if it takes you 100 seconds to do that. So here's how we're going to line this up. Remember, work is equal to change in kinetic energy. It's also equal to change in potential energy. No surprise there. All power is, we would abbreviate it with a capital P, so that's nice and easy to remember. Power is simply equal to your work divided by your time. In other words, it's equal to your change in energy divided by your time. That's all there is to this. And on your formula sheet, it is listed in both of these ways, just so that you remember. But it's saying the same thing, because work is equal to change in energy. So we'll just do a couple examples and wrap this up. So here's our setup. So get that drawn in. As you can probably guess, our goal here is to calculate the amount of power that it takes to move this object 20 meters in the time of 4 seconds. So if I want to figure out what that power is, remember, power is simply equal to work divided by time. And work is simply your change in energy. Now, which kind of energy should I use to figure out the work? Potential or kinetic? Kinetic, absolutely, because it's moving. So kinetic is the easiest thing to do here. So this is what we're going to be using to hopefully figure this out. So if I want to figure out my change in kinetic energy, I just have to take my information there and calculate it out. So remember, change in is final minus original. And then we would just plug those numbers in. Original velocity is equal to 0, so that means the entire original kinetic energy will be equal to 0. So let's see what we get. 1,250 joules. So that's equal to the change in kinetic energy. And we're pretty much there now. It tells us exactly how long it takes for us to move this object from left to right. And so all we do then is divide our change in energy by the time. And that gives us the amount of work. And 3 digits would be 313. It would come out to 312.5, whatever. If you're going to put units on this, anybody know what the units for power is? Joules per second is true, and there's actually another unit that we use when we combine those two.
Does it start with a W?
Yes, it does. Watts, absolutely. Well done. So now here's, even though this is kind of a simple thing, this is where things can just get a little tricky. You got to remember that this capital W is for watts. This capital W is for work. So just make sure that you realize when you're putting your units on power, that does not mean work. It means watts. Yes?
How come you subtracted? Is it because of the change in money?
Yep. When you're doing change in anything, it's always the final value minus the original. Other questions on this one? Okay, let's do another one. Pretty painless, huh? Compared with putting an object at rest on an incline of 40 degrees, calculate the normal force. Personally, when I went through this the first time too, I liked energy a lot better than force. It took me a long time to really digest force. They're both fun though, now. So this next example, we're going to talk about power again, and at the very end we're going to add a little wrinkle here. So we're going to use potential energy in this one. We'll say these two guys are hauling up a piano by a string, because that's just obviously the best way to do that. I'll put the keys in there. There, perfect piano. So they attach it to a string, and they're hauling it up to this guy's second floor apartment. So we'll put a couple numbers up here. We'll say it takes them 20 seconds to do this. So the question, of course, then is what power are these guys exerting as they lift this piano? So as they lift it, we're going to say it's originally 1 meter off the ground, and that when they get up to this level, it's 11 meters off the ground. This way we're not setting original energy equal to 0. Kind of helps us deal with that at least once. So if we want to find out power, we use the exact same procedure we used in the last one. Power is simply equal to work divided by time. And work is just change in energy. What kind of energy should we use here? Potential, absolutely, because we're moving upwards there. So, if I want to solve for my change in potential energy, once again, it's just final minus original. We put the little O next to the original height here, so that you remember that's the starting height. So we're just plugging numbers in there for our potential energy. So if you run that calculation, you'd get 14,700. If you're a scientific notation nerd, it would be 1.47 times 10 to the 4th. 1, 2, 3, 4. Yeah. So yeah, this would be your change in potential energy. So of course then, if you want to figure out what the power is, all you do is you divide that amount of work, or that amount of, that amount of work in joules, divided by your time. So it takes 20 seconds to do all this. And let's see where we land. 735 watts. That's the amount of power required. Now the final little wrinkle that I'm going to mention here is horsepower. You guys ever heard of horsepower? Yeah. Kind of feel bad for horses. Everything whenever you hear about horsepower, it's like 100 horsepower, 1,000 horsepower. This rocket ship has 1,000,000 horsepower. Kind of makes the horses feel like they're worthless now. Do we really need to keep comparing that it takes 1,000,000 horses to equal the power of a rocket ship? Anyway, so if this is what we have for our amount of work and our final power there, we can actually directly calculate what the horsepower is just by taking 735 watts and dividing it by a specific number. You can write this part in here. Horsepower is equal to the number of watts that you have, and we divide that by the magic number of 746. So all we do here to find that horsepower is divide our power divided by 746, and that gives us our horsepower, which comes out to 0.985. And that's what we would get for that. So combined, these guys are not quite doing what a single horse could do. So there you go, horses. Make you feel a little bit better. Questions on this? Alrighty.